last day we were seeing what are some of the problems where AI techniques can be applied. So it is not that it is very dramatically different from what we have learned so far in algorithms, but actually it deals with some special cases where we said that such problems are polynomially hard problem. And we thought of a rough scheme where we could see that many of the AI problems can be thought as a state space search problem. Okay, and this state space search problem can be solved by certain operators like moveGen, which will generate the neighborhood, and also goal test, which will tell you that whether you have reached the goal or not. Okay, so that's the idea. And what in this slide we are trying to tell is that essentially we want to develop a domain independent behavior. So basically what does that mean is that we can be working with a natural language processing problem, or we can be dealing with a computer vision problem, or we can be dealing with a route planning problem, a problem where you are assigning a car in Uber, right? So if you change your technique completely, then there is not much advantage. So when you say domain independent algorithm, so let's say you think about breadth first search, right? So whatever problem area you are working upon, if you can model the problem as a graph problem, you can apply BFS, right? So essentially that's what we are telling over here, that this moveGen and this goal test, these are domain independent functions. However, for each problem, how you are generating the neighborhood, that is going to be different. How you are going to represent your state, that is going to be different. Once you have set that up, like once you have set up what are the domain dependent things, right? So domain dependent thing is that what is the neighborhood, how will you represent a state, so these are domain dependent. Then one, you can apply your moveGen or goal test, which are actually independent of a domain, and you can proceed with those algorithms. So that's the idea. Okay, now let's look at this problem. Okay, so this is called as lion man cabbage problem. So AI has always been fascinated with games. AI has been always fascinated with puzzles. So this is a puzzle you might have all of you might have known. So here what you need to do is actually you need to transport a lion, a goat, and a cabbage across a river. Okay, so there are so there is a river. Okay, there is a river, and what you have is that on one side of the river you have a lion, right? You have a man, and you have a cabbage. Okay, and of course you have a boat also. So your task is to take these things to the other side of the boat. So you other side of the river. So you want to take all of them to the other side of the river. However, there are certain constraint. So what is the constraint? The constraint is that in the boat the man can carry only one thing. Okay. So firstly, of course, the man has to be there on the boat. Okay. And sorry. So there is another component: lion, man, cabbage, and goat. Okay. Okay. So the constant is that if you keep the goat and cabbage together where the man is not there. Okay. So if the man chooses to take the lion to the other side, then the goat will eat the cabbage. Okay. Similarly, if the man chooses to take the cabbage to the other side, the lion will eat the goat. So anytime lion goat combination or man goat cabbage combination cannot be kept at one side of the river bank if the man is not present. So it is also not possible that the man has taken the lion this side, right? Then the man has taken the goat this side. Okay, and he will come back. So it is not possible, because in that case the lion will eat the goat. Is it clear to all of you? So as we are discussing about state space search, first thing is how can I represent a state. So here I will invite opinion from you, that how will you represent a state. So state means you have to somehow formally represent this, right? That where they are, what is the start state, what is the goal state, like that. Can anyone tell me?
এটা বুঝতে পারলাম না, স্টার্ট স্টেট আর ওটা মানে এটা
মানে
কি বলতে চাই?
আমি স্টেটে কি করে এটাকে রিপ্রেজেন্ট করব? When we are talking about state space search, we have to represent it in terms of states. স্টেটটা তো আমরা বুঝতে পারলাম, we could understand it in normal language, that all in the starting state, all the objects that are there, the lion, the man, the cabbage and the goat are on the left side of the river. এটা তো clear? Okay, the boat is also on that side, right? Now this is your start state, and goal state is of course the right side, you will have all of them. But if
হ্যাঁ
you
সব
want to store it in a data structure, in a variable, how will you store this? Is the question clear to you now?
বুঝতে পারছি।
Okay, no guess.
স্যার চেষ্টা করতে পারি?
হ্যাঁ প্লিজ।
বলছি স্যার, যদি অ্যারে ইউজ করি আর অ্যারের একটা সাইডে আমি যদি মানে সেপারেটর বা কিছু এরকম রাখি, যে মানে ওই দিক থেকে এদিকে, এদিক থেকে এদিকে ট্রান্সফার করা যায়।
না এখানে না, ফার্স্ট থিং ইজ you should be able to separate the thing. Separate out the problem. So we are now just thinking about the representation. I am not discussing how will you how will reach the goal. Okay, so one of the thing is that I can use a structure like list. So you know what is a list, right? So let's say you have one list, and this list actually consists of two smaller lists. Okay, one is a left sublist, another is a right sublist. So maybe I can represent the start state as L M, these are the elements actually, L M C G B, right? C G B, and the other is a empty list. This is empty, right? And of course the goal state will be, this will be empty, the left list will be empty, and the right list will have all these elements, right? So this can be one representation, right? And there can be, and most importantly you can argue that, sir, is it required to have the boat over here? Is it not implicit that wherever is the man, right, there is the boat, right? So probably I may not represent the boat. So another represent can be just this LMCG. Okay, so now I don't know who it was talking, was it Kushal?
হ্যাঁ স্যার,
হ্যাঁ হ্যাঁ।
মানে আমি স্যার
So
মানে ডেটা স্ট্রাকচার ওয়াইজ এইভাবে ভাবছিলাম।
so another way can be that he is thinking of a separator element. So let's say I want to mention that the lion and the cabbage are on this side, okay, and there is a separator, this is also element, right? And we have a man and goat in the this side, right? So this can also be a representation of the representation of a state. So here this actually indicates that the other thing is on the other side, right? The rest of the things are on the other side. Is it clear? Right? And it is not.
sir.
So whatever states we have discussed, so these are not only, only possibilities. So there can be many further possibilities. But what I want to tell you is that whenever you have a problem like this, the first thing that you will have to think is how will you represent the start state and goal state formally, which you can, where a program can operate. Okay. So here the example is given like this, what we initially discussed, right? mg lcb and this then the empty parenthesis, right? And then goal state is empty parenthesis on the left side and then mg lcb on the other side. Okay, the first representation that we discussed. Okay, and then how can you generate the neighborhood state? So neighborhood state means, so always remember, neighborhood state means that whatever smallest step that is possible for you to take. So here what is the smallest possible step? You can take the boat from left bank to right bank, or right bank to left bank. Do you agree? So if I am at a current state, so what can be the different states that I can reach within one traversal from one bank to the other bank? Is it clear to you? So if I take something like this, that you have mglcb like this, so one thing can be that, so here I am not thinking of the constraints first. I am just reproducing all possible states. So one state can be, I have kept the lion and goat here and then cbm over here, right? Similarly, I can have gc over here and lbm over here. Similarly, I can have lion and cabbage on the left side and bgm on the other side. Similarly, I can have glc and mb over here, right? So these are different states that I can reach with one step. Okay, so these are my neighboring states. So if this is given as an input to my moveGen function, then it should return me these different states, right? So this is where the concept of moveGen is coming to play. Is this part clear to you? So once I go on expanding, I will check that I am reaching the goal state or not. When I will reach the goal state and I get a goal state, goal test equal to true, I will stop. So this is how simply it will work. Okay.
স্যার এখানে যেগুলো পেলাম সবগুলোই তো তাহলে সলিউশন হচ্ছে, এবার ওর মধ্যে থেকে ও যেই সলিউশনটা মানে সুটেবল হবে সেইটাই তো নেবে, তাই তো স্যার?
এরকম কিছু আমি বলিনি।
আচ্ছা,
there is no concept
solution to
there is no concept of there is no, his question is valid. His question is that out of the states that are getting generated, so in this particular case what is happening is that only this is valid, rest are not valid. But let's say there are more valid states here. So probably Orithro's question is that if I now have to go to the next state, which state I should go? Should I go here or should I go here?
Exactly sir, এটাই জিজ্ঞেস করছি।
Yes, I understood that. So it will depend on what kind of search you are doing, right? So if you are doing kind of a DFS search, okay, so probably you will pick up this one. So the data structure that you are using, if you are using a stack, right, so you will pick the state like that, and you will add the states left to right. Okay, all right.
ওকে স্যার, বুঝতে পেরেছি স্যার।
All right, so now there is another problem which is called as missionary and cannibal puzzle. So where the problem is that in one side of the river you have 3 missionaries and other side you have 3 cannibals. Okay, and they wish to cross a river using a 2-person boat. The boat can carry only 2 person. If at any point of time the cannibals outnumber the missionaries on either side of the river, they will eat the missionaries. Okay, so how can a sequence of boat trips be performed that they will get everyone to the other side of the river without missionaries being eaten? Okay, so again please understand that we are interested at what? We are just interested at the representation of the start state and the goal state. Okay, So now you have understood this with some part of lion, man, goat and cabbage. So why don't you try this one? The question is clear to all of you, right?
স্যার স্টার্ট স্টেটে রাখবো হচ্ছে M1 M2 M3 মানে তিনটে মিশনারিজ, আর C1 C2 C3 আর বি রাখবো যদি বোর্ডটাকে বি বলে ইন্ডিকেট করি।
এটা হচ্ছে
এটা
M1 M2 M3, this is your C1
C2 C3
3, okay,
অ্যান্ড বি,
and B.
আর সেকেন্ড সেটটা ব্ল্যাঙ্ক রাখবো।
This is your start state, and goal state is that. So
এইটা রাইট,
so essentially what you are meaning is that whatever is in the left side that you will keep, right?
এক্স্যাক্টলি, হ্যাঁ সেটাই থাকবে।
Okay, fair enough. So this is one representation. Any other suggestion?
এটা এটা উল্টাও তো হতে পারে, মানে বাঁ দিকে ফাঁকা থাকবে আর ডান দিকে না, না হবে না, অন্যরকম হয়ে
হ্যাঁ,
যাবে।
হতে পারে, কেন হতে পারে না?
হ্যাঁ মানে নদীর এক পার থেকে এপার, মানে ডান দিক থেকেও বাঁ দিকে যেতে পারে, বাঁ দিক থেকেও ডান দিকে যেতে পারে, সেদিকে গোল স্টেটটা তাহলে এক্স্যাক্টলি তার উল্টোটা হবে, তাহলে ডান দিকটা ফাঁকা হবে, বাঁ দিকটা ভরা হবে আর কি।
Right. Anything else?
Combinations of missionaries and cannibals to change হতে পারে।
মানে তুমি বলছো C1 টাকে আগে নিয়ে আসবো, M1 গুলোকে পরে নিয়ে যাব।
হ্যাঁ, MI CI টা CJ টা চেঞ্জ।
ওকে, সো
স্যার একটা জাস্ট ডাউট আছে, বলছি মিশনারিজ আর ক্যানিবালসটা কি মানে একই সাইডে আছে?
হ্যাঁ,
আচ্ছা,
আবার দুটোর মাঝখানে বোট আসতে পারে স্যার।
মানে
MIs তারপরে B তারপরে CJs।
না, সেটা ঠিক আছে। ওর যে রিপ্রেজেন্টেশনটা বলছে, ও বলছে আই এম রিপ্রেজেন্টিং দ্য পিপল দ্যাট আর প্রেজেন্টিং, they are present in the left side. So initially start state, by his logic it is fine, because he is saying M1 M2 M3 C1 C2 C3 and B are on the left side, and goal state he is saying the left bank is empty, so it's an empty array or empty list, so which is okay. আরো কেউ আনসার দিলে ভালো হয়।
আরো কি স্যার অপশন আছে, মানে অন্যভাবে রাখা যাবে?
আমি তো বললাম স্টেট স্পেস সার্চ পুরো ব্যাপারটাই খুব ওপেন। Okay, so one of the thing that you can think is that is there a need to differentiate actually M1 from M2, M2 to M3? এটা কি দরকার আছে? Is it required? বোঝা গেল প্রশ্নটা?
হ্যাঁ স্যার।
So can I do something like this?
330 মানে
তিনটে ম্যান, তিনটে ক্যানিবেল,
তিনজন মিশনারি, তিনজন ক্যানিবেল, 0 মানে boat is on the left side. In the next step it is 2 to 1. So 2 to 1 means that actually you have taken one missionary and one cannibal to the right side. So in the left side you have two missionaries and two cannibals, right? And in the right side you have the boat, so 2 to 1. Okay, similarly you can have 3 1 1 and 1 3 1, right? And this is not a valid state. Why not? Because here you have one missionary and 3 cannibals, so they will eat up. So these two can be valid states. তাহলে স্টেট রিপ্রেজেন্টেশনের প্রবলেমটা ক্লিয়ার হলো তো?
স্যার লাস্ট পার্টটা আমি বলুন 2131।
হ্যাঁ,
221 311 এটা কিভাবে হবে?
That what we are representing is that what is, so these two indicates this, the first two numbers indicate number of, the first number indicates number of missionaries in the left side, the second number indicates number of cannibals in the left side, the third number indicates which side the boat is. If it is on the left side it is 0, if it is on the right side it is 1. Is it clear?
Yes.
So all the neighboring states, you see the right side is 1 because the boat will go to the other side, there is no other option. So that is clear, the last number. Coming to the first two numbers, one common thing that you can see is that the addition is 4, all of them, right? Because the boat can carry 2%, right? And so here actually what you have done is you have sent one missionary and one cannibal to the other side, right side, so it is 2 to 1. Here what you have done is you have sent 2 cannibals to the other side, so all missionaries are here, 2 cannibals are on the other side. Okay, and the next is that 1 missionary is there and 3 cannibals are here, that means 2 missionaries you have sent on the right side, and naturally here the cannibals has outnumbered the missionaries, so they will eat them up. Okay,
স্যার তার মানে ক্রসটা শুধু থার্ডটাই তো হচ্ছে, বাকি প্রথম দুটো তো ভ্যালিড হচ্ছে।
হ্যাঁ প্রথম দুটো
Of
ভ্যালিড।
course.
ওকে ওকে
বুঝেছি স্যার।
Okay, so what we are going to do is we are going to make a very simple search technique. Okay, so the search technique starts like this. So we have a data structure open, okay, and we write a loop. So initially what we are doing is whatever is the start state we are adding it to open, while open is not empty, so first time you already have start, do pick some node n from open. So it is it is necessarily made little fuzzy, okay, that pick, what is the meaning of pick some node, but just assume that we are taking some node from open, okay, and then you are changing open, so you are subtracting or differencing this node n from open. Okay, so if you have nodes like 1 2 4 in open, and if you have selected 4, so essentially that means is now open has 1 and 2. Is it clear? So now you are doing a if goal test n equal to true, so the node that you have picked up, is it the goal? If yes, then you return n, else your open is open union move gen of n. So you have not got what was the goal, right? So what you will do is you will generate the neighboring states of this node and you will add it to open. Is it clear to you? Okay, all right. So now we will try to expand this and see.
স্যার নাম্বার 4 স্টেটমেন্টটা ওপেন এর মধ্যে অ্যাসাইন হচ্ছে ওপেন বাই এন, ওই জায়গাটা কি কাজ করছে একবার বলবেন?
It is not by n, it is actually open set difference n. So as I said that
আচ্ছা
that if you have picked if node n is 4 and in open you have 1 to 4, so next step open will have 1 and 2.
হ্যাঁ হ্যাঁ বুঝতে পেরেছি, ওইটা বাদ চলে যাবে। আচ্ছা ওইটা সেট ডিফারেন্স অপারেটর।
Yes,
আচ্ছা আচ্ছা
yes. Okay, so now let's say we have a node like this. So this is the start state, this is the goal state. Okay, now can you tell me that is there an issue with this algorithm? Okay, so let's expand this and see. So what we are doing is, so this is your open, okay, let's evaluate it very clearly. This is your open, so initially your open has the node s over here, right? So this is your open has s. Now what you are doing is naturally you will remove s as we discussed, and we'll take all the nodes that are reachable from s, right? Neighboring states a, b and c. So we are added a, b and c. So when there is a underline, that means that node is picked. So now let's say b is picked, so naturally b is removed, and you are seeing that what are the neighboring states of b. So neighboring states of b is neighboring states of B is S, right, A and D, right? So these are added. Okay, so you had AC, S and D are added. You see that? Now S is picked up. So again, when S is picked up, you have added A, B, C, A, C, D. Again, if you have picked up B, it will become S, S, C, A, C, D, A, C, D, like this. So what is the problem?
স্যার ট্র্যাপড হয়ে যাচ্ছে, মানে বারবার এস আর বি রিপিটেড হয়ে যাচ্ছে, বাদ বাকি কোনো
Yes.
নোট পিকটি হচ্ছে না।
Yes, yes. So there you can go in a loop. To put it very simply, you can go in a cycle, right? So what can I do in this case?
স্যার লাস্ট পোরশনটা দেখতে পাচ্ছি না, এস এ সিটি ফর
হ্যাঁ,
এস এ সিটি ফর এস এ।
এটা কি সবারই হচ্ছে?
না স্যার, দেখতে পাচ্ছি, অসুবিধা হচ্ছে না, পুরোটাই দেখতে পাচ্ছি।
ওকে,
স্যার এস এ সিটি এটার পরে কি বললেন?
এটা এক্সপ্যান্ড হয়েছে, আর তো কিছু নেই এর মধ্যে। বিটা আবার এক্সপ্যান্ড হয়েছে, বিটা এক্সপ্যান্ড হয়েছে।
আমরা আবার ওখানে ফিরে গেছি, রাইট রাইট, এবার
হ্যাঁ, so this is a problem. So what we can do, we can keep a track what we have, where we have gone, like the concept of visited. So let's introduce another data structure which is closed. Okay, so we start with having start in the open and then empty list as closed. So now what we are doing is, while open is not empty, pick some node n from open. So in the next step, first we are removing that node from open, which is fine, which we were doing earlier also. And now we are only adding, we are also adding this n to the closed. So that means we have already visited this node. And then we are also having the same thing. If goal test n equal to true, then return n. So this is the goal state, so return. Also, you are making open as moveGen n, and then you are not adding those ones which are already there in the closed. Are you seeing that? Just 1 minute. স্যার ক্লাস নিচ্ছি। হ্যাঁ স্যার, বলছি ক্লাস নিচ্ছি আমি, তাহলে একটু বাদে করব। ঠিক আছে স্যার, ওকে 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 okay, okay. So you can see over here, right, that we are removing those things which are there in moveGen, which are already there in close. So the things that you have already visited, that will not be added, right? So if you do this small change, right, so now if you evaluate this, so you will see that you start with S, then closed is empty. Now you expand S to ABC, right? So as you have already picked up S, so S has moved to closed. Now if you have moved, if you have picked up A, okay, so A has moved to closed now, and A has been expanded to BCE. Okay, so A has neighbors like S, B and E, but then S is already there, right? So B is already here in open, so you are having B, C and E. Okay, so similarly, you know, if you proceed like that, at one point of time, you know, you will pick up the goal state which is G and will stop there, right? So that is how you can reach the goal. Is it clear? Okay, now actually there are it turns out that there are two type of problem. One type of problem is called as a configuration problem, and another type of problem is called as a planning problem. So in configuration problem, you are merely interested to reach the goal, okay, and in planning problem actually you want to know that how you have reached that position. So one example that is often given, for the configuration problem is the 8 queen problem. Okay, that what is a good position in a chessboard where the queens are not compromising, right? So this is a configuration problem. Okay, and planning problem is that you want to actually, so this is like a root problem, so you want to go from a city A to city M. Okay, so what are the different intermediate cities you will go through to reach the city M? Okay, so is the difference between configuration problem and planning problem clear to you? Hello?
স্যার একবার বলুন একটু।
কনফিগারেশন প্রবলেম আর প্ল্যানিং প্রবলেমের ডিফারেন্সটা ক্লিয়ার হয়েছে?
আর একবার বলুন না, ওটা 8 কুইনটা কি বলেন? 8 কুইনটা
8 কুইন্স প্রবলেমটা তোমরা জানো তো, যে চেস বোর্ডে তোমরা দেখতে চাই যেটা এন কুইন্স প্রবলেম। এন কুইন্স প্রবলেম সেটা নর্মাল চেস বোর্ডে 8 কুইন্স প্রবলেম। ইউ ওয়ান্ট টু পুট all the 8 queens in such a way in the chessboard such that they are not compromising, right? So your goal is to find such a state. It is not, you are not interested to know how you have reached there. But planning problem is that you are reaching from maybe a city A to some city, another city. So you want to find out, because you want to ultimately solution should give you the path, right?
আচ্ছা আচ্ছা বুঝেছি।
Is it clear to everyone? Now the question is that the search technique that we discussed, actually will work for a configuration problem but not work for a planning problem, because what we were doing till now was we were picking up one node and testing and seeing that whether that is a goal or not, but it was no way storing the path. Are you understanding? So there can be some schemes by which you can change your search algorithm so that it can also work for planning type of problem. Okay, so as example, you can change your state representation like this. So what is happening, just look at this. So basically we start with having open as S. Okay, and then when you are expanding, actually you are appending your parent state also. So you are at S, the childs are A, B, C, so you are representing as AS, BS and CS. It is just a representation, nothing else. Okay, so when now you want to inspect, let's say node A, okay, when you are trying to explore node A, so you will have to have a mechanism to extract A from AS. So this is an extra function that we'll need. Are you understanding? So now from A, where all you can go? From A you can, so B is already there, right? And S is already there, so you can only go at E. So extension will be EAS. So this is how it is increased. Do you see that? Now out of this BS, CS and EAS, BS is picked up. Okay, so B has neighboring nodes as A and D. Now A is already explored, so naturally you have now DBS. Okay, so you have CS, which was already there, then you have DBS, and then you have ES. And let's say now DBS is picked. Okay, so if DBS is picked, now what is the neighbor of D? Okay, the neighbor of D is G. Okay, E is already picked up, C is already picked up, so only G will be added. So it is GDBS. Okay, and now when you extract the first node out of this GDBS, you see that it is goal, right? So if it is goal, it is now very simple. What you need to do is you just need to reverse this string, so which tells you that go from S to B, B to D and D to G. Is it clear to you?
Yes.
Okay, so let me still quickly summarize what we are trying to tell. What we are trying to tell is that the problem, the way we solved earlier using open and closed, was actually when we solved using open and closed was actually something called as a configuration problem. that we want to find out whether a particular state is goal state or not, which is fine, but we are not interested, or we were not interested to understand that what path was taken to reach from or go from start state to goal state. Okay. So this type of problem where we are interested about them, we call this as a planning problem. And for the planning problem, what we understood is that there is a need to change the way we represent the nodes. There is a need to change the way we represent the nodes. And a very simple scheme that we thought is that we will just append the parent to the existing representation. Okay, so when we have expanded AS into A, B and C, we have represented it as AS, BS and CS, right? So actually this will add more process, because every time what you need to do is you need to actually extract the first node, right? Because it is no longer A. You have to take out A from AS and then do the expansion. Are you getting it? But the advantage is when we actually get the goal state here, we can just reverse this representation and say that you go from S to B, B to D and D to G. So we are getting the path, and hence this representation is fine for a planning problem. Okay.
So, sir, actually, we are representing a node as a path.
We are representing not as a path, but we are representing it in such a way so that when we reach the goal, we can reconstruct the path. So this is not only one representation, so there are other representation also. Okay, this is a simple one, but you can always keep, apart from the first one, you may always keep the
PS or CS, right?
representation length as 2. Okay, so what you are doing over here is that you are doing a EAS. So instead of EAS, you could have made EA. So always your immediate parent should be there, but in that case you had to traverse this open, and you have to see that okay, EA, now you are getting A over here, so AS, that way you had to proceed. Are you getting me? Okay, so this is what I wanted to tell you. Now again, going back to what we were discussing earlier, right? So can you tell me that this is BFS or DFS? And assume that we are not making peak sum node. Okay, it is not peak sum node.
আমার মনে হচ্ছে ব্রেথ ফার্স্ট সার্চই হবে এটা।
Actually, it depends on, let's say you have 1 over here, okay, and you also have 3 at the same level, and now so these two are in open, okay, and now you are expanding 1 and you are having 2 and 4. So there are two options, right? One is already removed from open. So there are two options. First option is that you have 3, okay, 2, 4. So you added the child later. This is case 1. And second case is you have 2, 4 at the starting, okay, and 3 at the last, right? So you add the child at the starting. Okay, are you getting me? Right? So if you add the child first, that becomes depth first search, and if you add your or visit your same level nodes or neighbors first, then it is breadth first search. So if you change here, so here what is happening is the children are getting added later, right? So these are the children, right? So this is BFS. So if you have changed the order and made like, so you remove this, right? If you remove this and you make like union open, then it would have been DFS. Are you understanding?
হ্যাঁ স্যার।
So by this small change, actually you can change it from BFS and DFS. And here what you are assuming is that the head of the data structure is being picked up. So you can use stack and queue appropriately for storing this element. Okay, all right. So now let's again pictorially look at BFS and DFS. So essentially if this is your start state, right, and then you are expanding, this is your next neighbor, so you are applying move gen, these are your neighboring state, then you have you can apply move gen, and that's how it is now. This is called a search tree, right? This is a search tree. So DFS will move like this, right? So whatever is colored over here, right, grayed out, that means this is the order it is visited. So 1 to 2, 2 to 3, and like that, right? And maybe here is the goal. And look, in contrast, look at BFS. So it will start here, visit all the nodes at the same level first, then go to the next level. So it will go level by level, right? So that's why we call it as breadth first, right? Okay. So now let's compare them more. So if the search tree is like this and the solution is somewhere here, right, then BFS will reach here much quickly than DFS. You can understand. And if if the solution was here, then BFS would have taken a long time, but DFS would have reached much earlier. Okay. So there are certain characteristics by which we actually compare algorithms. So which are like completeness, time complexity, space complexity, quality of solution, and so on and so forth. Okay. So can you tell me what is the meaning of completeness?
রেজাল্ট পাবেই এরকম ব্যাপার, যে এখন খুঁজে পাবে একটা সময়।
Yes, sort of that. If a solution exists, then it is guaranteed to get the solution. Okay. So in terms of time complexity, both has comparable time complexity. So there is a quite what I would say quite complicated derivation of this time complexity equation, so which I am not going into. And space complexity wise, just intuitively understand that BFS will need to store a lot more elements, because it is every step actually number of nodes get increased exponentially. Are you understanding? That maybe here you had one node, then you have 5 nodes if the branching factor is 5, next you have 25 nodes, and so on and so forth. But DFS will increase linearly because you are adding one and then will add another 5 nodes, right? Are you getting me? So that's why many time when you have lot of states, DFS is advantageous. Quality of solution means that like which one will give you a closer solution to optimal solution. Optimal solution means you absolutely know the path, so A to D, D to G, but these are both exploratory algorithms, right? They are also called as blind algorithms, right? Uninformed algorithms. So they are exploring the solution space, giving certain very very fundamental trivial rules, right? So quality of solution, BFS tends to get shorter path to the solution naturally, because it doesn't give it doesn't do a jump, right? So it will sweep like this and move, right? Sweep like
এটা
this and
শর্টার
move.
পাথ তো কথাটা, মানে পার্ট লেখা ওখানে।
হ্যাঁ, পাথই তো বললাম। হ্যাঁ, এখানে পার্ট হবে না, পাথই হবে।
ঠিক আছে।
Okay, all right. So as I said, that DFS and BFS are blind search, okay, which are also called as uninformed search. So basically dhoro when we are exploring and let's say this is your this is a node, maybe somewhere here you are, right? Let's say you are at this node, okay, and let's say these are the neighboring nodes, right? This is a neighboring node, this is a neighboring node, this is a neighboring node, okay. And actually all these nodes will be equally probable to be picked up. Okay, any node can be picked up earlier. Okay, because there is actually no sense of order, so you cannot say that this is earlier. So you can follow some convention, but there is no sense of order between the neighbors actually, right? So if this is A, this is B, right? So it is not necessarily that I will pick A before B and I will pick B before A, right? Is it clear? So these are, you can say that these are equally probable to be picked up. It is random which one will be picked up. But if some way you have an idea about the goal, right? If some way you have an idea about the goal, what you can do is you can look at the neighboring states and comparing the neighboring states with the goal state. What you are doing? You are comparing the neighboring state with the goal state. Whichever is actually better compared to the goal, you can go to that state at the next. So maybe I am trying to look at how close this is to the goal. Okay, so let's say by in terms of closeness, this is 10. Okay, this may be 15 because it is away from the goal. Maybe this is 16, right? This is again maybe 10. Okay, and this is maybe 9 or maybe 8, and this is 9. So if some way I can establish such a notion in my search, naturally I will not go to 15, 16, 10. I will go and reach 8. Is it clear? So this is a question actually Orithro was asking at the start, right? So how can I
sir.
How can I actually bring this concept? How can I bring this concept of comparing the start state with a goal state? So this is a very important notion. Okay, and this type of search is called as heuristic search. Okay, so heuristic, heuristic is a term which means that it is a thumb rule. It's a thumb rule. So you are not sure about it. It may not work out at the grass level or actual level, grassroots level, but it will give you some indication. Okay, so let's say you are over here. Okay, let me go to the next slide and explain. So let's say we are doing a route finding problem in a city, and we are at a source position and we want to go to a destination position. So this is the source position and this is the destination position. Okay, so one simple heuristic function can be just this, that if this is represented in terms of x and y coordinates, so I am assuming that this is in a xy plane, so maybe this point I will represent it as x goal and y goal. Okay, and any point I will represent, maybe if I call that as point n, I will represent that maybe this one as x and y n. So if from our high school I know that if I draw a straight line and try to find the length of the straight line, I will do a x goal minus x n square plus y goal minus y n square and take a square root of that. Is it clear to you? Right? So this can be one of the heuristic functions. So what we are doing, so whatever we explained, that we are actually trying to find out how close a particular node is with respect to the goal state, right? And some other approach also can be that, so this is actually called as Euclidean distance. Okay, and some other distance also can be this one, x goal minus x n, you take a mod value plus y goal minus y n. So basically it is just the so let's say here is a point like this. Okay, so this actually gives you this distance, where the first heuristic function actually gives you this value, the second heuristic value actually is sum of the other two sides of the triangle, right? Is it clear to you? Okay, now what essentially you understand is there are two things that needs to be understood. First thing is that any heuristic function will take the current state and the goal state as the input. Okay, and there can be multiple heuristic functions. So as you see that you can use any of this, and if you think more, there will be more possibilities that will come to your mind, right? And they give an indication on the quality of solution. So what do we mean by that? We are meaning that we are giving an indication on quality, not a guarantee. Are you understanding? So can you tell me, for a root finding problem, from your common sense, that why this may not work well? Why, if I move from this to here, why this may not be a good decision? Can you tell me? This happens all the time when we, let's say you want to go from your university to Shelda, right? So why this may not work? Is the question clear to you? Hello?
আমি বুঝতে পারছি না।
না, কোয়েশ্চেনটা কি বুঝতে পেরেছিস?
স্যার,
না, আমি আগে শুনে নি
এটা
কোয়েশ্চেনটা
কি
সবাই
এরকম
বুঝেছে
হতে
কিনা।
পারে যে
আমি আগে এটা বুঝে নি কোয়েশ্চেনটা সবাই বুঝেছে কিনা। আমি
আমার বুঝতে অসুবিধা হচ্ছে।
এটা কি পড়াবো?
হ্যাঁ।
আচ্ছা, আর কেউ? প্রিয়াঙ্কা, কুশল?
স্যার আমার একটু অসুবিধা হচ্ছে।
হ্যাঁ স্যার বুঝেছি।
আচ্ছা, কুশলের অসুবিধা হচ্ছে। অনিকেত? ওকে, হিউরিস্টিক ফাংশনের ব্যাপারটা বুঝেছিস? আমি আগে কি করছিলাম, what we were doing was that I am at a particular node, I was applying move gen function on that node and generating the neighborhood node. This is clear to all of you? In BFS, no way. যেরকম if move is applied on this particular node over here, right, all these nodes are generated. So BFS will not differentiate these nodes. Are you understanding? BFS DFS will not differentiate these nodes. Okay. So actually heuristic function, what it tries to do is it tries to find the quality of these nodes. So it tries to find that among these nodes which one I should pick so that I will reach to the goal faster. And here heuristic function comes into play. So heuristic function checks that how close you are with respect to goal state if you are comparing between, let's say, these two nodes. So you see that okay, this is closer to this one, and how do you measure that? Using some heuristic function you get some value and you see this is better than this. Is it clear to you?
হ্যাঁ, এবার বুঝতে পারছি স্যার।
আচ্ছা, এইবারে প্রশ্নটা হচ্ছে I have got that this is the best node in terms of heuristic value, right? But still this may not be the best choice. Why this should happen like that?
স্যার, এটা কি হতে পারে যে এই হিউরিস্টিক ফাংশন দিয়ে এটা অলওয়েজ মানে ক্রো ফ্লাইং পাথ দেখায়, যেটা শর্টেস্ট বাট সেটা রিচেবল নয়। মানে আমরা হয়তো এই পয়েন্ট থেকে ওই পয়েন্টে,
সেটাই
সাপোজ
বলছি।
আপনি যদি রিয়েল টাইম,
হ্যাঁ, রিয়েল টাইম সিনারিও সেটাই শুনতে চাইছি, বলো।
হ্যাঁ, যেমন হচ্ছে মনে করেন আপনি এখান থেকে, আমি ক্যালকাটা ইউনিভার্সিটি যাব সাপোজ রাজারহাট থেকে, আমার এখান থেকে 6 কিলোমিটার দেখালো ইন দ্য ক্রো ফ্লাইং পাথ, বাট যদি আমি অ্যাকচুয়াল রাস্তা দিয়ে যেতে যাই থ্রু উবার বা ওলা, সো অ্যাকচুয়ালি আমার রোডের যে বেন্ডিং বা যেগুলো আমায় কভার করতে হয় সেটা সাপোজ 8 কিলোমিটার।
ওটা হয়তো তুমি আরো কঠিন করে ফেলছো। হ্যাঁ, কিন্তু এরকম তো হতেই পারে, যেরকম আমাদের ক্ষেত্রে আমাদের ইউনিভার্সিটির পাশেই একটা ক্যানেল রয়েছে, রাইট? কিন্তু ক্যানেলের কাছাকাছি কোনো এক্সিট নেই, মানে যেটা নিয়ে তুমি গাড়ি দিয়ে বেরোতে পারো, হয়তো হেঁটে বেরোতে পারবে, গাড়ি নিয়ে বেরোতে পারবে, এরকম কোনো এক্সিট নেই। তাহলে হতে পারে হয়তো এই যে ক্যানেলটা রয়েছে, ব্রিজটা এইখানে, রাইট? তাহলে আমার এই নোডটা দিয়ে যাওয়াটাই বেটার।
রাইট স্যার, রাইট।
এবং সেম ইজ দ্য কেস ফর, মানে সেরকম হতে পারে দেয়ার ক্যান বি ওয়ান ওয়ে কামিং আপ, হ্যাঁ, uh, there can be traffic condition, কোনো রাস্তা থাকতে পারে যেরকম হয়তো you have a choice between bypass and maybe a by lane, so bypass is a better option maybe. Huh. So that's the reason heuristic function. So what is our understanding is that heuristic function will give you an indication of the quality. Okay, so that's what it's mentioned over here. So let me highlight this. So it gives an indication on the quality of the solution. And we also understood that there can be multiple heuristic functions. Okay, so actually we will stop today. So let me quickly summarize. Okay, so what we essentially discussed is that first of all we understood that there is something called a state space search in context of AI, and this state space search can be rolled out using two operators. One is this move gen, which generates given a state generates neighborhood states, and goal test, which tells that whether that is the goal state or not, right? Okay, now we understood that how for a couple of problems we understood how to represent a state formally and all that, and we looked at BFS and DFS. Okay, how a simple search technique can be modified into BFS and DFS. Then we realized that BFS and DFS are essentially blind search problem, which are also called as uninformed search problem. And as AI problems typically will have much more states than normal computer search problems, right? So we cannot really work with blind search problems, right? So that's where we understood that there is something called as a heuristic search. What heuristic search does? Heuristic search actually uses a heuristic function. What is a heuristic function? Heuristic function actually gives you quality of a node with respect to the goal, right? So if you are generating your neighbors, it can help you break tie, or it can help you decide which state, which neighboring state will go to. Okay, so that's kind of what I have to cover. Now if you have any questions, you can ask that.